Assalamu alaikum. Welcome to the next lecture. In this lecture, we are going to start a new topic of the new unit. It is known as mechanical design of overhead transmission line. Mechanical design actually it means the analysis of sag and tension. In this case, we will try to see how this sag will affect uh, the design of transmission line and how we have to uh, appropriately calculate the tension on the conductors and how they are related to each other. First, let us define what is a sag. A perfectly flexible wire, that is a conductor, of uniform cross section and strung between two supports at the same level will form a catenary. As we know that whether it is a chain or a cable, a catenary is the curve that an idealized hanging chain or cable assumes under its own weight when supported only at its ends. So such type of shape of cable or chain is known as catenary. This also, the conductor will also form a catenary. However, if the sag is very small compared to the span is actually the length between the two supports, its shape approximates a parabola. So in that case, we'll approximate its shape as a parabola and we can solve this by using the parabolic equations. So this is the introduction to this sag and what is actually its definition. It is actually a difference in level between the point of supports and the lowest point on the conductor, that is known as sag. The conductor will sag or dip because of its own weight, as is hidden in the definition of the catenary. So it is because of its weight, it dips or it sags from the idealized position. Now you can see it from here. These are two poles or supports, and we have a conductor which is hung from this end to this end. You will see that ideally it should be in this form, that is, it should be quite horizontal from this point to this point, like this dashed line. But because of its weight, you will see that it will uh, be like this, or it will sag. And the difference between this, that is a point of support, and the lowest point in the conductor is known as sag. The difference between the lowest point and the ground is known as ground clearance. So it is because of this ground clearance we need to design the transmission line in such a way so that this minimum point should be at a height which is greater than this specified ground clearance, because we know that because of the certain voltage of the conductor it should be above the ground level, that is by certain height, and when it is above this ground by a certain height, so it will be safe. So based on that, or keeping the mind the minimum distance or specified ground clearance, we need to design the transmission line in such a way so that this sag will be minimum, or it should be in such a way so that its lowest point should be at a height greater than this minimum specified ground clearance. So one more thing, that if the conductor is in horizontal position, where uh, we are doing in such a way, we're stretching the wire in such a way, we're applying a tension to this conductor in such a way so that it becomes horizontal. You'll see that there will be two forces applying on this conductor. One is the tension that will be in the horizontal direction. Uh, Here the tension will be in this direction, horizontal direction, and here the tension will be in this direction. And you will see that its other force will be the weight, which will be on the vertical direction. When it is in horizontal direction, the one force will be acting exactly in the horizontal direction, another will be acting in the vertical direction. You'll see these two forces will be independent of each other. They will not cancel each other. There will not be any equilibrium in that case. So that is why it will always form such type of a catenary or such type of a curve. So that the tension, which is slightly inclined to the horizontal, it will have its horizontal component and vertical component. Vertical component will balance the this weight component, and this horizontal component will balance the horizontal component on this side. So in this case, when it sags a little bit from the horizontal position, it will be definitely in the equilibrium because all the forces will then cancel out. So the main factors in the design and stringing of the conductors on the supports are conductor load per unit length. So, or in general, it may be uh, taken as conductor weight. That's what conductor load. Conductor tension. That is the tension that occurs between this point and this point. The span. Span means distance between the two horizontal supports. Horizontal distance between the supports, and temperature. As temperature increases, you will see that the sag will increase. The length of the conductor will increase and its tension will decrease. We'll come to this after completing these things. For determining the conductor load, or we can say weight, the factors that need to be considered are weight of the conductor itself, weight of the ice or snow clinging on the conductor, because when the ice on the conductor uh, is there, its weight will increase and there will be more sag. It will dip more because its weight due to this snow will increase. Wind blowing against the conductor, this will also increase its weight. Wind blowing. So keeping these factors in mind, we'll try to first uh, do the sag calculations. So we'll assume that the conductors which are suspended between the supports, they are at the same level. That means these two, this point and this point, they are at the same level. So I represent this by this form, slightly zoomed version of this. Let us say this is the origin, and W, the small w, is the weight of the conductor per unit length, and I will assume this Cartesian coordinate where this assumes the x-axis and this is the y-axis. So at any arbitrary point which is at a distance of x from this origin and y, or we can say this point is point x and y, its horizontal distance from this origin is x and vertical distance is this y. So let's say this point is p, x and y, and at this point we know that tension will be perpendicular to this curve, and let's assume this tension is T, and this S is actually the length of this conductor from this O to P. The total length of this conductor, which will be definitely greater than the span is defined as capital L, and the total length of the conductor, you can see from here to here it is L by 2, that means total length will be small l. So let O be the lowest point of the catenary curve and it can be considered as origin. L is the span or horizontal distance between the supports in meters, that is from this point to this point. Small l is the length of conductor, again it will be in meter, that is this is the length of the conductor. W is the weight of the conductor per unit length, kg per meter, and T is the tension of the load in kg, that is tension of this conductor in kg at point P, and H is the tension at origin. This is the tension at origin. So at this point you will see that there will be no vertical component, and you can see the tension actually is a force. It should have been in Newton because we are not keeping in the mind the value of the g, that is acceleration due to gravity. You will see that it will cancel out in each expression. So here we're only using T divided by g, that's the acceleration due to gravity. Its unit will always be kg. So we are here calculating or using the tension or force in terms of kg only. Now coming to this, when we resolve this t into its horizontal component tx and vertical component ty, you can see it will be ty and tx. And the distance from O to S is S, and total weight from O to P will be equal to this W into S, because W is the weight per unit length. Total weight will be equal to W into S, and it will be in kgs. And when we find something in kg over here, we are uh, assuming that to be equal to force. Now this is one force, vertical force, this is one vertical force. This is the horizontal force, this is the horizontal force. And in equilibrium, the two horizontal forces which are opposite, they will be same. That is Tx will be equal to H, Tx will be equal to H, and Ty will be equal to this V or Ws. So this is at the equilibrium point. One more thing, you can see from here to here we have S, and S corresponds to this Y, and this is X. When S is an infinite small distance, or we can say when S increases by a small amount of ds, this dy increases by a small amount of dy, and dx increases by a small amount of dx. So in that case, that can be represented by a triangle. This is ds, this is dy, and this is dx, and this is theta. And you will see that this theta and this theta, they will be same. So in that case, this tan theta will be equal to dy by dx, which is equal to from this triangle, because ty is equal to v and tx is equal to h, it will be equal to v by h, where v is equal to ws, that is this. So from this triangle, this ds square is equal to dx square plus dy square, and dividing both sides by dx, it will be equal to ds by dx whole square, which is equal to 1 plus dy by dx whole square. So simplifying this, and put the value of dy by dx as ws by h, it comes out to be ds by dx square is equal to 1 plus ws by h whole square. So now separating this dx and ds, you'll see that ds by dx is equal to square root of 1 plus ws by h whole square, and then this dx to be taken to the right, and ds is to be divided by square root of this. That means dx will be equal to ds divided by square root of 1 plus ws by h whole square. So x will be equal to integral of ds divided by square root of 1 plus ws by h whole square. So this is actually this we get from integrating this equation. Now we'll integrate this. So when we integrate this, the right hand side of this, we get x is equal to h by w sine hyperbolic inverse ws by h plus k. Because if we have minus over here, it would have been h by w sine inverse only. There will not be hyperbolic term sine inverse ws by h plus k. But since it is plus over here, the formula is this. So it will be sine hyperbolic inverse ws by h. This h by w comes from this, because when we integrate something, so we are integrating with respect to s. So when we integrate, the coefficient of s has to be divided. So when we divide the coefficient of s, when we divide w by h, it comes out to be h by w. Now this is the value of x in terms of s. So where k is the constant of integration, we can find it from the initial value or boundary conditions. At this point, you will see that when x is equal to 0, this s will also be equal to 0. It will be at this point. So that means when x is equal to 0, s is equal to 0. This whole term will be equal to 0. This whole term will also be equal to, that means k is equal to 0. So x is equal to h by w sine hyperbolic inverse ws by h. We are actually interested to find the s in terms of x. So when we do that, this x will be equal to, sorry, s will be equal to, we multiply this will be wx by h, and then sine multiplied by h by w. That means s is equal to h by w sine hyperbolic wx by h. This is the important formula which gives us the value of s in terms of x. At any point from this point to this point, we can get the value of value of s at any intermediate point. And the value of s at x is equal to L by 2 will give us uh, half length of the we can say a conductor, half length of the conductor. So in that case, we will be able to, when we get the half length of the conductor, we can get the full length after that, after multiplying the two. So this is very important because we can get any intermediate value of s. So at x is equal to L by 2, s is equal to small l by 2. And x is equal to L by 2 because this s will increase to this point. That means this will be L by 2. So L by 2 is equal to h by w sine hyperbolic WL by 2h. So multiplying this equation by 2, I get this L is equal to twice h by w sine hyperbolic WL by 2h. This is the total length of the conductor, which is actually hung from this point to this point. Or we can write as L is equal to twice h by w, that is the same, twice h by w. When we expand this term, it will be 1 divided by 1 factorial WL by 2h plus 1 by 3 factorial WL by 2h whole cube plus all other higher terms. So we'll neglect all other higher terms. So when we multiply this to this h and h will cancel out, this w and w will cancel out, this 2 and 2 will cancel out. It will be only L. Similarly, for this case, it will be 1 by 6. It will be 1 by 6, and this 2 cube will be 8, and 6 into 8 will be equal to 48. And here it is 2. That means 2 and 2 ones are 224. That will be 1 by 24. Here 1h and 1h will cancel out. It will be only h square. Here w and w will cancel out. It will be only w square. So it means this term will be equal to w square. This should be L cube. W square L cube divided by 24 h square. So please try to correct this. No, this is L square because it has taken L outside this. It will be actually L plus W square L square divided by 24 h square. L plus W square L cube divided by 24 h square. When L is taken outside, it will be 1 plus W square L square divided by 24 h square. So I hope you understood this. And this is the total length of the uh, conductor. So we actually neglected all other higher terms because that will contribute very small value to this. Now this was the calculation of the length of the conductor. We'll now try to find out the value of the sag, calculation of the sag. So from the figure we know dy by dx is equal to ws by h. So dy by dx you will get by multiplying s w by h, you will get dy by dx. From here you can see s is equal to this value. When you multiply w by h, you will get sine hyperbolic wx by h. That's what I have written over here. Sine hyperbolic wx by h. So from here dy will be equal to sine hyperbolic wx by h into dx. This dx is simply multiplied over here. When you integrate it, you will get integral of sine hyperbolic wx by h into dx, and its integration will be definitely cos. It's called h by w cos of wx by h plus k1. So this k1, that is the constant of integration, can be found out in the same manner as we have done it in the previous equation. So when x is equal to 0, y will be equal to 0. Putting x is equal to 0, this term will be equal to 1. So it will be equal to h by w. That means 0 is equal to h by w plus k1, or k1 is equal to minus h by w. So therefore, this y is equal to h by w cos hyperbolic wx by h minus 1. This is also important equation which gives us the intermediate value of the y from point O to from this support point. Now the curve of the above equation, that is this, is known as catenary, and it can be written as. So this curve, that is when we try to find out the curve uh, by varying this x and calculating the value of y and plotting them on the xy coordinate, we get the curve known as catenary curve. So when we expand this cos term, there will be only even terms. It will be equal to 1 plus 1 by 2 factorial w x by h whole square plus all other higher terms minus 1. This 1 and 1 will cancel out. It will be equal to 1 by 2 w square x square divided by h square. When we multiply this h by w, it will be equal to w x square by 2h. And this is one of the most important equation, and we are going to use mostly this equation in the coming sections. So this is actually the vertical distance of the conductor with respect to x. As we change the x, we'll get the vertical distance. Now, the sag of the conductor of span length L between the supports on the same level is at x is equal to L by 2. You can see the sag is actually this D. And this equation gives us a vertical distance. This equation gives us a vertical distance. Here, the vertical distance is 0. As we go from this point to this point, you can see this vertical distance increases. And this vertical distance, or this D, will be at x is equal to L by 2. When we put, this is the original equation without simplification. So when we put x is equal to L by 2, in that case y is equal to D. So D is equal to h by w cos hyperbolic w L by 2h minus 1. When we simplify this equation to this is h by w, and there will be only even terms as was the case in the previous equation. It will be 1 by 2 factorial w x square by 2h minus 1. This 1 and 1 cancel out. And when we put x is equal to L by 2, you will get w L square by 8. This is the equation of the sag, which will be there when there are two poles supported at the same level. You can get this equation by putting x is equal to L by 2 here also. When x is equal to L by 2, this comes out to be L square by 4. And when we multiply 2 here, it will be W L square by 8h. So that is what we have got from here. So this is the equation of the sag. Now we'll calculate this H, calculate maximum horizontal tension H. It's actually maximum horizontal tension H. It can be calculated from this triangle. We know that T is equal to, from this triangle, T will be equal to square root of H square plus V square. Or taking H common, it will be equal to H into square root of 1 plus V by H whole square. Where we know that from this triangle, this V by H will be also equal to dy by dx whole square, and this dy by dx is equal to sine hyperbolic wx by h, and when we put 1 plus sine hyperbolic square wx by h, it will be equal to cos hyperbolic wx by h. So here, in terms of square root of this, that is square root of 1 plus dy by dx whole square will be equal to square root of 1 plus sine hyperbolic wx by h whole square, and that will be equal to cos hyperbolic wx by h. So t will be equal to h cos of wx by h. This equation will also give us the value of this tension at any point x, arbitrary point x, or intermediate point from from O to this point. So whereas the total tension in the conductor at support will be at x is equal to L by 2. When x is equal to L by 2, total tension will be equal to h cos of W L by 2h. So when we expand this term, it will be equal to 1 plus 1 by 2 factorial WL by 2h whole square plus all other higher terms. Neglecting other terms, we get t is equal to h into 1 plus 1 by 2 factorial WL square by 2h. So from this equation, this is actually a non-linear equation, or we can say quadratic equation only, because we are neglecting the higher order terms. Quadratic equation in terms of h. So because we are calculating the h, t may be given. So this will be a non-linear or quadratic equation. We have to use this equation to solve for h. So in this case, we will be getting the value of the h. So in summary, we have actually three equations to be uh, considered. One is the length of the conductor. Length of the conductor will be equal to L into 1 plus W square L square divided by 24h square. Vertical distance or sag, this is the vertical distance, that is Wx square by 2h. This is very useful equation. We are going to use it quite often. And when x is equal to L by 2, we will get the sag. That sag will be equal to D WL square by 8h. and the maximum tension, that is H, that has to be calculated by using this equation. We're not going to find out T, we are going to find out H over here. So this is what for the time being we are going to do, and I hope in this class this is sufficient. We'll proceed further in the next class. Thank you.